Hi everybody, Professor Jamer here. So today we're going to talk about topic 16, which is the equilibrium model. So before, whenever we were talking about forces, we know that F net is equal to ma, where our net force is going to be equal to a vector, and then we have mass times the acceleration. So normally what we have to do is we need to split everything up into components. So we have F net x is equal to max, and then F net y is equal to may. So today we're going to be focusing on a couple special cases where our net acceleration is going to be equal to 0, but we still have something moving. So you're asking, how can we have something where we have no net acceleration for a couple of these problems? Well, we just have a constant velocity. So that means our object is moving, but since it's a constant velocity, our forces are still somewhat balanced. So here we have an example. So we have a car of weight 15,000 newtons, and it's being towed up a 20-degree slope at a constant velocity. Friction associated with the rolling tires is negligible. So let's first draw everything in terms of the diagram that we see here, but let's make it a little bit more interesting. So for this, we have an inclined plane. We have the car right here, and we know the force due to gravity is straight down. So this is our FG. And so then we draw our normal force straight up from the object, and then we have this little helper line. This is our angle theta, and it matches the angle theta from our incline. And through our geometry, we know that those angles are equal. So we have the tension being directly up from the object itself. So the best way to solve this problem is to rotate our axes. We've previously talked about rotating our axes in a different lecture. And so what I can physically do is I can say that this dot is where I live. This is the car. And then I draw the tension only in the x component. I draw the normal force only in the y component. And then the only force that has multiple components is the force due to gravity. So if I kept everything this way, then I would have to take the cosine and sine of the tension, the sine and cosine of the normal force, and it would become a lot messier. By flipping my axes, I can say that my tension is only in the x, my normal force is only in the y, and my gravitational force is the only thing that I have to split up into the FGX and then the FGY. So here I have the gravitational force in the x is going to be equal to negative mass times g, and my x component's opposite to the described angle, so then that's going to be sine of theta, and then my FGY is going to be equal to minus mg cosine theta. So if we want to talk about the tension force, if we want to solve for the tension force here, how would we go about doing this? So we know that m times g, since it's going to be the weight, is going to be 15,000 newtons. So this is the magnitude of the force due to gravity. So whenever we set up our problem, we have to think about the x and y component. So we have F net x is going to be equal to the tension minus mg sine theta. And so we see that this car is moving up at a constant velocity. So I'm going to say that we are equal to max. In this case, since we have a constant velocity, ax is 0. So then our equation is equal to t minus mg sine theta, and that's equal to 0. So then we have the force due to tension is equal to mg sine theta, where our theta is equal to 20 degrees, and we have mg is equal to 15,000 newtons. So that's going to be 15,000 times sine of 20 degrees. And whenever you plug it into our calculator, we see that we get 5,130.3 newtons. So this is the tension in the rope when we're pulling the car up the incline with a constant velocity. So whenever we have a car of weight 15,000 newtons is being pulled up at a constant velocity, and we want to find the normal force. So if we wanted to find the normal force, how would we go about doing that? So we would use the same process as before, where we have to diagram our x and y components, but since we're using the same values, it's a little bit less complex as the first one. So now, whenever we're writing this out, we have the same force diagram. So let me copy that. And let me paste it right here. Okay, so we have the same force diagram as before. So here we have the normal force minus FGY is equal to MAY. Here it's not moving in the y direction at all, since we're placing all our velocity in the x component whenever we rotate our axes. So there's never been any motion in the y direction with the way that we drew our axes. So then we have Fn minus Fgy is equal to 0. So then we have the normal force is equal to mg cosine theta, since we found that Fgy was mg cosine theta. And so then we have the normal force is equal to 15,000 cosine 20 degrees. So then our normal force that the car experiences is going to be equal to 14,095 newtons. And so that is how we can do one of these problems, especially with regards to the inclined plane. So now for the next problem. So this is going to be a little bit different of a flavor, but we still have to go through the example here. So we have a model rocket with a mass of 800 grams. So whenever we say grams, we know we have to convert to kilograms, since kilograms is the proper unit of physics. And it has a weight of 7.84 newtons. So then we know that Fg, if we were to just look at it, is 7.84 newtons. And I'm just going to make sure that it's equal to the right weight. So we just do 0.8 times 9.8. And yes, that's right. The person writing this problem didn't make a mistake. And so then we see that the thrust is going to be equal to 24.0 Newton, and the time that thrust is in play is 4.50 seconds, and then the rocket is going to be in free fall. So now let's look at phase one. So before burnout. So we need to find the acceleration of AY. So in the first phase, let's say that this is the center of mass of the rocket. We have F thrust, we have Fg, and we know that we have some acceleration in the Y. So then we can say F thrust minus Fg is equal to mass times the acceleration in the Y by using Newton's second law. So then we have 24 minus 7.84 is equal to 0.8 times AY. So when we plug this into our calculator, we get an acceleration of I get an acceleration that is equal to 20.2 meters per second squared. So that is our first part. So for phase 2 it's basically a free-for-all problem. So we're trying to figure out what the maximum altitude reached by the rocket. So we want to find the velocity. So we want to find the displacement the rocket first moves up. So we want to figure out this altitude, which we'll call delta y1, which is where the thrust ends. And then we know that the rocket is launched, with then an initial velocity, since we'll have a final velocity at this point, which will be equal to the initial velocity up here. And then it's going to go up, and then reach this maximum altitude, and then go down. So the first step is to find delta y1. Here we have a constant acceleration because we have a force. And so then we have essentially delta y1. We're going to assume that there is no initial velocity right here. So v01 is equal to 0. So then we have v01 times t plus 1/2 ay t squared. So there's no initial velocity, and we want to find delta y1. And so that's going to be equal to 1/2 times 20.2 times 4.5 seconds squared. So the first half of our problem is just saying that delta y1 is equal to 204 meters when we plug that in. So now we need to find delta y2 while the object is in free fall in order to get to the maximum height, which is just going to be y1 plus y2. So here, before we find delta y2, we need to find the initial velocity of the second leg, the time it's under, or we can say that whenever it reaches up here at the maximum height, the velocity final is equal to 0, and then we can use velocity final squared is equal to velocity initial squared plus 2a delta y2, where this acceleration is going to be minus g since we are in free fall. So then we have v02 is going to be equal to v0 initial for the first leg plus our acceleration of the first leg times time, not squared. And then we can say that our initial velocity of our second leg is going to be equal to 20.2 times 4.5 seconds, which is going to be equal to 90.9 meters per second. And then we can say that this is going to be our initial velocity of the second leg. So then for our kinematics, we have 0 squared is equal to 90.9 squared plus 2 times negative g times delta y2. And so we have essentially 90.9 squared is 8262.81 is equal to, that's going to be negative 19.6 delta y2, and delta y2 is then going to be equal to 421.6 meters. So after the thrust turns off, the rocket goes an extra 421.6 meters. And then we know that the maximum altitude is going to be equal to delta y1 plus delta y2. And that's going to be equal to 204 plus 421.6. And so that is going to lead us to a total quantity of 626 meters whenever we have just 3 significant figures. And so that is how you can do that free fall problem right there. So if you have any questions about topic 16, let me know. And thank you so much for paying attention, and just